This problem says find the limits if they exist. And here are two different limits. If you notice very closely, there's little plus and minus symbols up and to the right of the value. And we'll talk about what that means in a minute. But this is pronounced the limit as x approaches -3 from the right of f of x. And this is the limit as x approaches -3 from the left of f of x. And the function f of x is a piecewise function. It's equal to 9 over x squared if x is less than or equal to -3. And it's equal to 4 plus x if x is greater than 3. So if you remember the regular definition of the limit, which is written like this, see there's no subscript, no superscripts here, just the limit of f of x equals L. If this is the function, we're saying that for every positive value of epsilon, however small, for each epsilon, there exists a delta such that if the absolute value of x minus c is greater than 0 or less than delta, what this means is that if the value of x is in this open boundary, but not necessarily right at c. So this function could have no value right at c, but it could, but we don't care about the value right at c. But this means that for every epsilon, you can crank this as tiny as you want, but for each one there will be an open boundary around c such that if x is in that open boundary around above or below c, then the value of the function, the difference between the value of the function and this limit L, will be within that region epsilon. This is the regular definition of the limit. And the key part that will distinguish it from a regular limit and a one-sided limit will be this part right here. Just remember, as we're talking in the next section, about how a regular limit has an open boundary that includes c and can have values of x above and below c. So now let's look at a limit from the right, as it's called. Let's see what problems we run into if we try to say that a limit exists where there is nothing of the function to the left of the limit. Here's the function f of x equals the square root of x. And if we say that, yeah, the limit is 0 because it goes down to 0 on this side, but to be strict, we're saying the regular definition of the limit is this for all epsilon, where epsilon is a positive value. There is a delta such that, and this is regular limit definition, the absolute value of the difference between x and, in this case, 0 is greater than 0 or less than delta. That means that it's within delta above or below. Well, you can't really say that it could be on that side. So this, using the regular definition of the limit, is not true to the situation when there is no definition of the function to the left. How do we modify this in the case where there is an open interval greater than the limit value? Not limit value, but the value of x. What this gets changed to, actually the type of limit you're talking about is from the positive side. It means coming from this side because this is the positive x direction. So you put this here, and now what you have to say is for all x greater than the c value, in this case specifically the 0, it's only the open interval greater than the target value and less than the target value plus the delta. So to put it generally, the definition in general, the limit as x approaches some value c from the right of f of x equals L means for all positive values of epsilon, there is a delta such that if x is greater than c and less than c plus delta, then the absolute value of f of x minus L is less than epsilon. So that's the limit coming from the right. Instead of saying the difference, the absolute value between 0 and x minus c is less than delta, now the proper interval to specify is between c and c plus delta. Here's an example of a limit from the left, where you're coming from the more negative direction, but there is nothing to the right of the target value. In this case, the function is the square root of c minus x. The largest value that the x can be so that the function has a real value is c. Because if x is anything greater than c, then this is negative and the solution is no longer real. But in this case, the open interval for the limit as x approaches c from the left, because the value of the c is the largest value it can be. The square root of c minus x for every epsilon greater than 0. Now there exists a delta such that if x is greater than c minus delta and less than c, now this is the open interval of the antecedent of this implication, then the absolute value of the function, the square root of x, of c minus x, minus the limit value, in this case 0, is less than epsilon. So given these new definitions for the open intervals, where for every epsilon there exists a delta, we can work out the same types of limit theorems as we work these coming problems. I encourage you to look more at the differences between this and this. Whoops. That would be a mistake. This is from the left. Oh. This is from the right. So with these different types, you can define a general limit with an open interval including but not necessarily at C, but not at C. And this is from the left, and this is from the right. But the same limit theorems, you can prove one-sided versions of them, which we will use with these following problems. So getting back to the original problem, plotting the original function, which is a piecewise function, you can see that for the values including -3 and below, the function takes this graph. And for the values greater than -3, it takes this. And in this particular function's case, you notice that these two functions do happen to have the same value at -3, so the graph of the function doesn't have any breaks in it. But we were asked to figure out the limit as x approaches -3 from the left of f of x. So we know that this is talking about the open interval to the left of -3. And so we look at the function and we see that this time what we should replace f of x with is 9 over x squared. And as I said before, you can prove for yourself that the regular limit theorems work. Now this is a rational function. This is a constant which you can pull out. So you can make this 9 limit x approaches -3 from the left. Now you've got 1 over x squared. And since x squared is a polynomial, you can just plug in the value. So we've got 9 over -3 squared. -3 squared is 9. So 9/9 is 1. So that means that the function from the left, it approaches 1. Now let's do the limit as x approaches -3 from the right. Now this is the part of the function that is to the right of -3, so you can make this 4 plus x. And we know the limit of a sum is the sum of the limits. The limit of a constant function is the value 4, or the limit of 4 as x approaches -3 from the right is 4, and the limit of an identity function is just the value at the limit. So what this ends up being is 4 plus -3, which is the same as 4 minus 3, which is 1. So the limit as x approaches -3 from the right is also 1. But in this problem, we've seen how to look at one-sided limits and how to understand what is meant by the notation here, and also that the same types of theorems as in regular limits can be applied to much simplify the work of solving these. This problem says find the limit if it exists, the limit as x approaches -10 from the left of x plus 10 over the square root of x plus 10 squared. So I encourage you to look at this and pause the video and first of all think, what does this function look like? One thing is, whenever you see the square root of something squared, what is that equivalent to? It's like the same as saying the absolute value of. x plus 10, right? Because something squared is always positive. And when you take the square root, you only mean the positive square root. If you want to talk about the negative of a square root, you always have to put this. But we could just as easily replace all of this with this. So we could write this: the limit as x approaches negative 10 from the left of x plus 10 over the absolute value of x plus 10. These two are the same. Now, think about this function. What does this function look like? If you need to graph some points, what is a critical value for this function? Think about where this function is not defined. Where does this function have a 0 in its domain? Because division by 0 is undefined. At negative 10, right? So let's put a bit of a, let's sketch the graph. Let's say that negative 10 is right here. So let's say what values to the right of negative 10, what is the sign of this? Say at x equals negative 9. At negative 9, this would be a positive value because negative 9 plus 10 is 1. In fact, anything greater than negative 10 is going to be positive. The denominator is always going to be positive. And they have the same magnitude. So at negative 9, the top would be 1. And the absolute value of negative 9 plus 10 is 1. So this would be 1 over 1, which would be 1. All values would be 1, right? How about x equals negative 11? Well, the absolute value of negative 11 plus 10 would be negative 1. The absolute value of negative 1 would be 1. What's the value of negative 11 plus 10? It's negative 1, right? The same thing for any value here, it'll be negative something over the same magnitude, but positive. So look at this function. Everything to the right of negative 10 is 1. Everything to the left of negative 10 is negative 1. And this is, of course, undefined right at negative 10. So visually, if we're on the function coming from the left and we're approaching negative 10, for any value of epsilon, we can get in on this open interval between, but not including negative 10 and negative 10 minus delta. What is the value going to be within epsilon of? It's going to be negative 1, right? So that's the answer to that problem. And if you were coming at it from the right, the limit would be positive 1. This is a case where a function has different values of one-sided limits. This function says sketch f of x and find the limit as x approaches n from the right of f of x and the limit as x approaches n from the left of f of x, where n is some positive integer. It's in the set of positive integers. And here's the function f of x. It's equal to x if x is equal to n, and it's 0 everywhere that x is not equal to n. So how would you sketch this? Let's put a couple of coordinate axes here. This is x, y. Looking at this function, let's say that n is some value. We won't even go on and specify which specific number it is. Let's just say it's right there. Now, if this is x, this is n on the x-axis, and x and y have the same scale, which is a good assumption, then n on the y-axis, we could draw it about right here. So, what does it say here? That x is equal to x when x is n. So here's n. At this value, the function's value is n, just at that one point right there. And everywhere else, I'll put an empty dot. The function's value is 0. So we can sketch it by just drawing. Like that. Now, see if you can, on your own, sketch the value or figure out the value of first of all, if x is approaching n from the right, which of these do we take? We're not on n because the open interval that we're taking is between n and some n plus delta, right? So if we're talking about this interval right here, we would use this one. X is not equal to n. And the function in that interval's value is 0. Very easy. The limit of a constant is the constant, right? So the limit as x approaches n from the right is 0. Now, let's talk about the limit as x approaches n from the left. Clearly, we can tell this is also, the function also 0. So in this case, interesting thing is the limits from both sides are equal to 0, but right at that point, the function's value is not 0. And this problem says find the limit as x approaches -3 from the left of f of x, and the limit as x approaches -3 from the right of f of x if they exist. And f of x is 1 over 2 minus 3x if x is less than -3, and this cube root of x plus 2 if x is greater than -3. So which open interval, and hence which type of function, applies for from the left? Which of these applies for values less than -3? This one, right? This is where you would really rather use the limit theorems than start over from the definition of the limit, right? We know that this type of function, this is a polynomial, so it's a rational function. We just want to plug in -3 and hopefully not get a value that is not in the domain of the function. But if we plug in -3 right here, 1 over 2 minus 3 times -3, this is 1 over 2 plus 9 is 1/11, right? So the limit from the left is 1/11. I think you know what to do for the limit from the right. We just want to plug in -3 right here. -3 plus 2 is -1, and the cube root of -1, an odd root of a negative number, does exist. What's the cube root of -1? It's -1. So now you see how to apply which part of a piecewise function if you're doing one-sided limits. This problem says find the limit if it exists. The limit as x approaches 0 from the right of 1 over x. So let's take a sketch of this function. We know that for positive values of x, the function is positive. And for very small values, it's very large. For very large values, it gets very small. It never reaches 0. Same thing for negative values. For large negative values, it's very small. For small negative values, it's very large. So what interval are we talking about here? X approaching 0 from the right, so not including 0, but we could say from 0 x to 0 plus delta is just delta. But is there any specific finite value that it approaches? No, it just gets greater and greater without bound as x approaches 0. So this limit does not exist. Because it increases without bound. Yep. This problem says prove if the limit as x approaches c from the left of f of x equals L, and the limit as x approaches c from the right of f of x equals L, then the limit as x approaches c of f of x is equal to L. So this is a proof that is related to showing that when the limits are the same on both sides, then that's the limit without qualification. How would you prove this? What would you start with? Would you start with the definition of the limit? Let's write the definition. Let's actually draw a type of drawing right here. What I'm going to do is I'm going to draw for the limit as x approaches c of f of x equals L. Now this is the domain. And this is the range. This is and this is C plus delta C minus delta. What is this drawing basically telling us? It's telling us for any epsilon above or below L, there is going to be a delta above and below, so that if X is anywhere in here, it will hit in this range right here. Now, let's put right here, except we don't guarantee that if X equals C, there is a value. So I'm going to put that empty circle saying this is an open interval bounded on the left by C minus delta and on the right by C plus delta, except the value of C is excluded from this open interval. Okay, this is a regular limit. Now, if I use this drawing to show then what is our interval that we're saying anything launched from within this interval will land within this interval, right? By the definition of the limit from the left, we're saying that if X is within the open interval C minus delta to C, not including C, then the output of the function will be between L minus epsilon and L plus epsilon. What is the limit as X approaches C from the right? What do I put right here? Think about it. This is the unbounded interval from C to C plus delta, right? We're saying that if the value of X is anywhere between C and C plus delta, the value of f of X will be between L minus epsilon and L plus epsilon. Now this, we're given that we've got this and this, but if we combine these two intervals, we do get the open interval from C minus delta to C plus delta, not including C. So that's a graphical proof. You could also state it using interval notation.